Let's look at section 12.4, solving exponential and logarithmic equations. Question 1, let's solve 3 raised to the 3x minus 2 is equal to 81. The first step is to get the same base. That's our strategy. We want to get the same base. On the left, this is 3 raised to the 3x minus 2. On the right, I want to rewrite 81 with a power of 3. And you can check with a calculator 3 to what power is equal to 81. That is 4. We know 3 to the 4th is equivalent to 81. And since they have the same base and they're equal to one another, then we can say that the exponents are the same. I can write 3x minus 2 has to be equal to 4. And so I can add 2 to both sides. 3x is now equal to 6. I could divide both sides by 3, and x is equal to 2. If we're not sure about the solution, we can always substitute it into the original equation. We can say 3 raised to the 3 times 2 minus 2. Is that equal to 81? If we do the work, we know 3 times 2 is 6. 6 minus 2 gives me 4. On the left is 3 raised to the 4th power, and it is 81. So we can always check our work if we want to make sure this problem is correct. Let's look at example 2. Again, the strategy is to try to get the same base. On the left, we have a base of 9, and on the right, we have a base of 27. It's going to be very difficult to rewrite 27 with a base of 9. This is impossible with a whole number. So we can't use this strategy. We have to pick a different base. If you look on the left, it's a base of 9. On the right is a base of 27. But we can rewrite both of them with a base of 3. I can change 9 as 3 squared, and that whole thing on the left becomes 3 squared raised to the 4x minus 1. On the right, we have 27, which I can rewrite as 3 cubed, and that is raised to 2x. In this case, the base is not 9 or 27. We choose a base of 3 so that they can be the same. Now we can distribute this 2 through the exponent, and we can multiply this 3 with the 2x. This gives me 3 raised to the 8x minus 2 is now equal to 3 raised to the 6x. Since the bases are the same, we can equate the exponents. 8x minus 2 is now equal to 6x. I can add the 2 to both sides. This gives us 8x equals 6x plus 2. We can subtract 6x to both sides now. 2x is equal to 2, and if we divide both sides by 2, x equals 1 is our solution. In example 3, again, the strategy is to get the same base. On the left, we have a base of 4. On the right, a base of 32. I want to ask 4 raised to what power is going to give us a 32? 4 squared is 16. 4 cubed, that is 64. And so we cannot make a 4 raised to a whole number equal to 32. So this strategy doesn't work. Let's pick another target base. I'm going to guess 2. And that actually works. So we'll say 4 can be rewritten as 2 squared raised to the 3x minus 1. On the right side, we can do 2 to the 5th power will give me 32. And that's raised to the x plus 2. Let's distribute the 2 now. This is 2 raised to the 6x minus 2 is equal to 2 raised to the 5x. Redistributing again. 5 times x is 5x. 5 times 2 gives us 10. Since they have the same base, and they're both equal, that implies that the exponents must be the same. 6x minus 2 has to be equal to 5x plus 10. I could subtract the 5x to both sides. And we'll also add 2 to both sides. 6x minus 5x is x. And on the right we have 10 plus 2, which is 12. This is a good solution. In example 4, we have 25 raised to 2x minus 7 is equal to 125 raised to the x plus 4. If you thought that you can rewrite 25 raised to a power equals to 125, it doesn't quite work. So we're going to have to pick a different target base. I want the same base, so let's pick a base of 5. 25 can be rewritten as 5 squared. And that's raised to the 2x minus 7. On the right here, 125 is equivalent to 5 cubed, and we'll raise that to the x plus 4. Each of these now has a base of 5, but we'll simplify by distribution first. This on the left is 5 raised to the 4x minus 14. And that's equal to 5 raised to the 3x plus 12. And this is through distribution. Since the bases are the same, I can equate the exponents. 4x minus 14 is now equal to 3x plus 12. Let's subtract the 3x to both sides, and we'll add 14 to both sides. This gives me x equals 26. The one-to-one property of logarithmic functions. If we have log base b of r equal to log base b of s, this implies that r is equal to s. This also goes backwards. If r equals s, that also implies that the log base b of r is equal to log base b of s. How is this important? Well, it says if you're taking the log of a function and it's equal to another log of another function with the same base, well, then you can remove the logs. That's what it's saying. We can take the logs away if they're the same base. And so we can try these problems now. It says give an exact answer and then round to the nearest thousandths. We want to solve 3 raised to x is equal to 12. Now I want to get the same base, but you'll quickly realize 3 to what power gives you 12 is not really doable without a calculator. And it's very difficult even with a calculator. So what we're going to do instead is use the property of one-to-one for logarithmic functions. It states that if r equals s, then I could take the log of both sides. And that's what I'm going to do here. I could take the log of the left side. I could take the log of the right side, and this will still hold true. According to our exponent rule, I can bring the power to the front. This is x log of 3 equals log of 12. I can now solve for x by dividing both sides by log 3. We'll divide both sides by log 3. And that divides out. I am left with x is equal to log of 12 divided by log of 3. Please, please don't make the mistake of reducing the 12 with the 3. These are inside a set of parentheses. You have to do the log of 12 first, then divide by log 3. You can't reduce the 12 and the 3. This is our answer in exact form, but you can always use a calculator. And if you use your calculator, let's figure out what this is rounded to 3 decimal places. This is equivalent to approximately 2.262. A tip for using your calculator is don't forget those parentheses. You could type this in decimals, but don't forget those parentheses. In example 6, I am first going to isolate that exponent. Let's isolate that exponent first by adding 9 to both sides. 4 raised to the x minus 5 is equal to 12. And here we cannot get the same base, so we'll start by taking the log of both sides. The reason I want to take the log of both sides is so I can bring down that exponent. That x minus 5 is now in the front of my equation. We have x minus 5 times the log of 4 is equal to the log of 12. I can solve for x by dividing both sides by log 4. I'll divide both sides by log 4. I'm extra careful with my parentheses because that's how the calculator is going to input our result. And so we have now x minus 5 is equal to log of 12 divided by log of 4. I can add the 5 to both sides. And here's my solution. X is equal to log of 12 divided by log of 4 plus 5. This is a good solution. If you want a decimal version, this is equivalent to approximately 6.792. If you look at your textbook, they will use different logs to solve for the exponent. You could use natural log, or you could use log with base 4. So it doesn't matter which one you use. You could use log with base 4 to solve for x. You could use log with base 10. You could use natural log, that's with base e. It will still work out the same. Let's try another problem. Let's look at example 7. And this time I'm going to use natural log. Again, it doesn't matter what you use. You could use natural log, you could use log, and the textbook prefers to use log base 7 because this problem has a base of 7. Either of those will work out fine. I'm going to stick with natural log, and other results are going to be similar. Let's start by subtracting the 8 to both sides. This is 7 raised to the x plus 2 is equal to 30 minus 8 gives me 22. I'll take the natural log of both sides. We'll put a parenthesis so the reader knows what's going on. And the x plus 2 here gets to go into the front because of the power rule. We have x plus 2 times the natural log of 7 is equal to the natural log of 22. I have to divide both sides by the natural log of 7 because it's attached with multiplication with the x plus 2. So let's divide both sides by the natural log of 7. That reduces that. We have x plus 2 is now equal to natural log of 22 divided by the natural log of 7. I can finally solve for x by subtracting 2 to both sides. X is now equal to the natural log of 22 divided by the natural log of 7 minus 2. Don't forget to include the parentheses, especially when you're entering this solution into the calculator. And we can finally solve for x here, round it to 3 decimal places. It's 0.412. This is a good solution, and this is a good exact solution as well. In example 8, let f of x be equal to 13 raised to the x plus 8 minus 22. I want to solve f of x equals 108. Do not confuse this problem with finding f of 108. We're not substituting the 108 into x. We're replacing the f of x with 108. This becomes 108 equals 13 raised to the x plus 8 minus 22. Now I could solve for x by isolating the exponent. Let's add that 22 to both sides. (108) plus 22 gives me 130 equals 13 raised to the x plus 8. We can now take the natural log of both sides. The natural log of 130 equals the natural log of 13 raised to the x plus 8. I can now bring that exponent up into the front. Again, just like in the previous problem, I could use natural log of both sides. I could use log of both sides. Or in the textbook, you'll find they use the natural log, or actually log base 13 to both sides. And that just makes it a little bit easier because we have a base of 13. But then again, it doesn't matter what you use. I'm going to stick with natural log. We have the natural log of 130 is equal to x plus 8, bringing that exponent to the front, times the natural log of 13. We can solve for x by dividing the natural log of 13 to both sides. And again, don't feel tempted to reduce 130 and 13. You can't do it. They're inside their own separate logs. We have the natural log of 130 divided by the natural log of 13. And that's equal to x plus 8. We can subtract 8 to both sides. And here's our solution. Our solution is x is equal to the natural log of 130 over the natural log of 13 minus 8. This is an exact answer. And if you wanted to, you could always check the work with a calculator to get a decimal answer. If we use the calculator, you should get x is equal or approximately equal to negative 6.102. This is the approximate decimal answer. In question 9, let's solve 3 times e raised to the x minus 4 plus 7 equals 31, and we'll round to 3 decimal places. For this example, we'll start by isolating the exponent, so that means we're going to subtract 7 to both sides. This is 3 times e raised to the x minus 4 is equal to 31 minus 7, which gives us 24. I will divide both sides by 3 to isolate that exponent. And this is e raised to the x minus 4 equals 24 divided by 3, which is 8. Let's take now the natural log of both sides. I recommend we take the natural log of both sides because we have a base of e. Now this is very important that we use natural log, and you'll see why in a moment. If we take the natural log of both sides, we can bring that x minus 4 to the front. The x minus 4 is in the front times the natural log of e, and that's equal to the natural log of 8. What is the natural log of e? The natural log of e is equal to 1. So I can actually ignore this part because we're just multiplying by 1. Again, the natural log of e is equal to 1. That's something we should remember. And that makes our life really easy. because this is now x minus 4 is equal to the natural log of 8. I can add 4 to both sides, and now here's our solution. X is equal to the natural log of 8 plus 4. And if you look at the decimal approximation for this, you would get x is about 6.079. In example 10, we'll solve logarithmic equations with more than one logarithm. In this example, you have to remember that if you're solving logarithms, you have to check your work. We have to check our work or it doesn't count. In example 10, we want to solve the natural log of x squared minus 2x minus 19 is equal to the natural log of 5. The first step is to realize they have the same base. This is both a base of e, and since they have the same base and they're both equal, we can use the one-to-one property of logs, which states you could take the log of both sides or you could remove the logs of both sides. That means I can equate x squared minus 2x minus 19 is equal to 5. And I know how to solve this. This is just a quadratic. Let's subtract 5 to both sides. X squared minus 2x. Negative 19 minus 5 gives me negative 24 is equal to 0. Let's try to factor this. This factors as x minus 6 times x plus 4, and that's equal to 0. And so we have two possible solutions. X could be equal to 6 or x could be equal to negative 4. But you have to check your work to make sure these are good solutions. So I need to check. And let's check that in the original equation. We'll plug in the natural log of 6 squared minus 2 times 6 minus 19. Is that equal to the natural log of 5? 6 squared is 36. Negative 2 times 6, that's negative 12, minus 19. And if you check, it is true. This is the natural log of 5 equals the natural log of 5. So that means x equals 6 is a good solution. Let's try negative 4. We have the natural log of negative 4 squared. I have the parentheses around the negative 4. 2 times negative 4 minus 19. Is that equal to the natural log of 5? This is the natural log of 16 plus 8 minus 19. And so, if we look at this carefully, it's true as well. So the natural log of 5 is in fact equal to the natural log of 5. Both of these answers are good, but we have to check because this is a logarithmic equation. It's a logarithmic equation. In example 11, we will start by taking away the logs. Again, they have the same base. They're both base 10. They're equal to each other. We can use the one-to-one property of the logs to remove the logs. And so x squared plus 15x minus 30 is equal to 2x. Again, I'm removing those logs using the one-to-one property of logs. We can remove the logs on both sides. Subtracting 2x to set this equal to 0, and hopefully we can factor this. X squared plus 13x minus 30 is now equal to 0. And luckily it can factor as x plus 15 times x minus 2 equals 0. That means x could be equal to negative 15 or x could be equal to positive 2. but I have to check, unfortunately, since this is a logarithmic equation. And we'll check x equals 2 first. Let's check our work. I want to know if log of 2 squared plus 15 times 2 minus 30 is that equal to log of 2 times 2. On the left we have the log of 4 plus 30 minus 30 is that equal to the log of 4. On the left it's clearly log of 4, on the right is log of 4. So the work checks out, and that means x equals 2 is a good solution. What about log of negative 15? Now we have to check x equals negative 15. Again, we'll use the original problem. We have log of negative 15 squared plus 15 times negative 15 minus 30. Is that equal to log of 2 times negative 15? So let's simplify this. And if you check carefully on the left, you're going to get the log of 15 squared on the left. If you use a calculator, you would get this is the log of negative 30, and on the right you get log of negative 30. And a lot of students will think, oh yeah, this is a good solution, but no, this is a bad solution. X equals negative 15 is a bad solution. Why is it a bad solution? Well, look at what's inside. This is a negative. You cannot take the log of a negative number. Recall the graph of a logarithmic expression is from 0 to infinity. You cannot take the log of a negative, so that means negative 15 was not a good solution. As soon as you notice that the argument is negative, just stop and throw out that solution. It will not work. A negative log cannot happen. Let's look at example 12. Again, I am going to remove the logs since they have the same base. We'll remove the logs and equate the arguments to each other. X squared plus 5x minus 8 is equal to 2x plus 2. I can now set this equation equal to 0. We'll start by subtracting 2x to both sides, and let's also subtract 2 to both sides. This gives me an x squared plus 3x minus 10 is equal to 0. And fortunately it factors as x plus 5 times x minus 2 is equal to 0. So we have two possible solutions. X could be equal to negative 5 or x could be equal to positive 2. We have to check our work. Now don't just throw out the negative 5. You have to check both of them. And negative 5 could work. Sometimes it does, sometimes it doesn't. Don't throw it out just because it's negative. We'll check log base 3 of negative 5 squared plus 5 times negative 5 minus 8. Is that equal to log base 3 of 2 times negative 5 plus 2? On the left, you'll notice this is a log base 3 of, you will get a negative 8 on the left. On the right, you get log base 3 of, again, negative 8. This tells me that x equals negative 5 doesn't work. Again, it's because the argument is negative. You cannot have a negative argument. X minus 5 does not work. You can check x equals 2 on your own, and it does work. So let's make sure you check that on your own. X equals 2 is a good solution. Example 13, again, since they have the same base, the base of e, I can set 5x minus 3 equal to 3x plus 5. There's no quadratic term here. That means I can just subtract 3x to both sides, and we'll add 3 to both sides. This gives us 2x is equal to 8. And solving for x, we have x is equal to 4. Now we have to still check our work. Let's check it in the original. You always have to use the original. The natural log of 5 times 4 minus 3, is that equal to the natural log of 3 times 4 plus 5? On the left we have the natural log of 20 minus 3. Is that equal to the natural log of 12 plus 5? And yes, that's true. Both sides are natural log of 17 equals natural log of 17. So x equals 4 is a good solution. In example 14, we're going to solve logarithmic equations with only one logarithm. Recall, log base b of x is equal to y implies b raised to the y is equal to x. To solve these equations, you always have to convert to exponential form. I'll start by converting it to an exponent. The base is 7. The power is the answer to the log. So this is 7 to the 1 equals x squared minus 3x minus 3. I can subtract the 7 to both sides because we all know 7 to the 1 is equal to 7. You have 0 equals x squared minus 3x minus 10. And so this does factor as x minus 5 times x plus 2. Which means we have two possible solutions. X could be equal to 5 or x could be equal to negative 2. Let's check our work. Log base 7 of 5 squared minus 3 times 5 minus 3, is that equal to 1? 5 squared is 25. Log base 7 of 25 minus 15 minus 3, is that equal to 1? Well, this is log base 7 of 7. This is true because 7 raised to what power gives you 7. Well, that missing number, remember, is the exponent, and the log is always the answer to the exponent. So in this case, it's true. 7 to the first is in fact equal to 7. So log base 7 of 7 is equal to 1. This is a good solution. Let's check the other solution. We'll check if log of negative 2 squared minus 3 times negative 2 minus 3, is that equal to 1? Again, I'm using the original problem. This is log of a base is 7, so don't forget that. This is negative 2 squared, which is 4. Negative 3 times negative 2 is positive 6 minus 3. So that gives us the same result. Log base 7 of 7 is equal to 1. That's true. And so even though this is a negative solution, it is also a good solution. In example 15, same strategy. We'll convert this to an exponent. 3 is the base. The exponent is the answer to the log. 3 squared is equal to x squared plus 10x minus 15. 3 squared, that's 9. And now I can subtract the 9 to both sides to solve for x. Let's set this into a quadratic that's equal to 0. And now we can try to factor this. It factors as x plus 12 times x minus 2. And that means we have two possible solutions. X could be equal to negative 12, or x could be equal to positive 2. I have to check both of these, and I want you to do that. I want you to check both of these. And you will realize that both are good solutions. So please check this on your own. I want you to plug it in, check it on your own, because that's what you'll have to do on the exam. You'll need to check these are good solutions, and they are good solutions. In example 16, we have an issue. We have two logarithms with an addition between. That means I have to use the product rule. Recall log base b of x plus log base b of y. I can actually multiply the arguments together. This is log base b of x times y. I can rewrite this as log base 2 of x times x plus 4, and that's equal to 5. I can simplify this using distribution. This is log base 2 of x squared plus 4x equals to 5. And so now I could use the exponential form of this. The base is 2, the exponent is 5, and it's equal to the argument x squared plus 4x. 2 to the 5th, that's 32. 32 is now equal to x squared plus 4x. Again, we'll set this equal to 0. Subtract 32 to both sides. I have 0 equals x squared plus 4x minus 32. And so I can actually factor this as x plus 8 times x minus 4. And that means we have two possible solutions. X could be equal to negative 8, or x could be equal to positive 4. But you have to check your work. You can't just accept this answer. So let's check our work. The first one is negative 8. I have log base 2 of negative 8 plus log base 2 of negative 8 plus 4 equals 5. Stop there. This does not work because you have a negative. This fails. X equals negative 8 fails. That's a bad solution. I don't even have to go any further. Inside a log is a negative answer. We stop there. But you got to check the other one as well. So let's check 4. And again, we'll use the original problem. Log base 2 of 4 plus log base 2 of 4 plus 4, is that equal to 5? 2 to what power gives you 4? That's 2. The answer to the log is the exponent. This is log base 2 of what gives us 8? 4 plus 4 is 8. 2 to what power gives you 8? Well, that's 3. So this is in fact true. Log base 4 is equal to 2. And log base 2 of 8 is equal to 3. So this is in fact a true statement, which means we only got one good solution, and that is 4. We have to throw out x equals negative 8. That doesn't work. In example 17, there's a negative between two logs, and that means we'll have to use the quotient rule. Log base b of x minus log base b of y is equivalent to log base b of x divided by y. And so I can rewrite this as log base 5 of an 8x plus 5 on the top divided by an x minus 10, and that's equal to 2. Since we only have one log, we can convert it using our exponents. I can rewrite this as an exponent instead of a log. So let's rewrite this as 5, that's our base, raised to the power of 2 should equal 8x plus 5 over x minus 10. 5 squared, that's 25. 25 is equal to 8x plus 5 over x minus 10. Let's multiply both sides by x minus 10. And there you go. We have it becoming a little bit simpler. This is now 25x minus 250. I got that from distribution. And on the right we have 8x plus 5. We'll subtract 8x to both sides. And then we'll also add 250 to both sides. 25x minus 8x, that gives me a 17x. And on the right here we have 255. Dividing both sides by 17, I have x equals 255 over 17. And that means x is equal to 15. Now this is not a good answer until you check your work. But if you do check it, it does work out. This is a good solution. I'll check it with you so you know how to do it. We'll look at the original equation and replace all of these x's with a 15. We have log base 5 of 8 times 15 plus 5 minus log base 5 of 15 minus 10, is that equal to 2? 8 times 15 plus 5 gives me 125. We have log base 5 of 125 minus log base 5 of 5, is that equal to 2? Well, 5 raised to what power gives us 125? That's going to be a 3. This is equivalent to 3. 5 cubed is equal to 125. So log base 5 of 125 is equal to 3. And log base 5 of 5, that's 1. And so this is in fact true. 3 minus 1 is indeed 2. So x equals 15 is a good solution. In example 19, we have 2 logs on the left and 1 log on the right. We'll start by using the product rule to combine the left side together. This is x minus 4 times x plus 10 using the product rule. And on the right we have log base 4 of x plus 26. Since they both have the same base, we can actually remove the logs. This is x minus 4 times x plus 10 equals x plus 26. We're almost there. You have to actually FOIL this out. I get x squared plus 10x minus 4x. This is minus 40 equals x plus 26. We'll collect like terms. This is x squared, 10x, and negative 4x together gives me 6x minus 40 equals x plus 26. We'll subtract the x to both sides, and we'll also subtract the 26 to both sides. I have x squared plus 5x minus 66 is equal to 0. And so you can see this factors as x plus 11 times x minus 6 is equal to 0. So we have 2 possible solutions. X could be equal to negative 11, or x could be equal to positive 6. But you have to check your work. in order to know which one works. And if you check carefully, you will realize by plugging in these numbers, the negative one does not quite work out because you have a negative inside the argument. So x equals negative 11 does not work, but I want you to check on your own x equals 6. That one will work. That one is the only good solution we have.